Hello, everyone, and welcome to our webinar on the pumping test interpretation using AquiferTest. Starting our subject of today, what I'll do is I'll first cover a little bit of the theory related to pumping tests. To some, it might be a refresher, while to others, there may be something new in it. And the reason we cover the theory is because, of course, we don't think of any software as a black box. So we really believe in understanding and learning what the software do before actually using it. So this is where we are going to start from. Pump tests then are an important component of hydrogeological studies, any hydrogeological assessments. We use these sort of tests to assess things like interference from pumping wells on hydraulic head of aquifers, surface water bodies, interference from pumping between abstraction wells, also to assess things like production capacity of wells, as well as aquifers. In terms of hydrogeological assessments specifically, they are very useful tools that we have to determine parameters such as transmissivity, storativity, hydraulic conductivity, and aquifer anisotropy. First of all, I'd like to make a brief distinction between pumping tests that are used to characterize an aquifer, so an aquifer test, versus a pumping test, which is more focused on assessing the well itself, which would be then a production test. So when we talk aquifer test, we are really thinking about hydrogeological studies, characterizing and defining the aquifer parameters, mainly transmissivity and storativity. And this will typically, or I would say almost always, at least one observation well. That means we pump one well and we monitor the variation in the water head on a second well. And these tests, they will have a minimum duration of 24 hours, but many times we would like to run them longer to assess things like boundary conditions and really think in terms of the sort of longer term impacts of pumping in a given system. Now, the production test is more focused on assessing the performance of the well itself. So we start by looking at what's the maximum flow that we can get from the well, as well as the relation between pumping rates and well efficiency. We typically do this for new wells, the ones where we don't have previous information on their pumping capacity, well losses, etc. And we do that by running step tests, which are the ones on the chart that you see on the right, where we pump the well at different rates and we see how tendency or how the trend of the drawdown curve functions at each stage. And typically these are shorter time wells. So a step test, you may run 3 or 4 stages of 1 hour each, or depending on the aquifer, you may extend that to 2 hours. So they tend to be shorter. So what an aquifer test consists of, there are a number of things that we need to measure. As I mentioned, we will have the pumping well and at least one observation well. In the figure below, what we see are 3 observation wells. So we will measure the discharge from the pumping well, discharge over time. We need to know the distance between the pumping well and the observation wells, and we will monitor the drawdown at each observation wells. And of course, we'll write down the testing times and the time where each reading is taken. Of course, nowadays, and in fact, for a while, we already have had the tools, data loggers, like the ones I showed at the beginning, to assist us on these tests, and that gives us a lot more flexibility and control over the test itself, as well as improving the quality of the data that we get. Well, in terms of measuring flow rates, there are different systems we can use. The best one, or the simplest one, will be to use a flow meter, like this one here at the bottom. But of course, if you are doing a first test in a remote site, you may need to adapt to using another system like a weir, or well, like a device like this where you have a pitot tube attached to the discharge pipe. And of course, depending on the flows, we can also do the volumetric method, which essentially means filling up a container and seeing how long it takes to fill up that container with the known volume. And like I said, water levels, we can measure them manually, but really what we want to do is do that automatically using our sensors. Turns the test itself a lot more efficient and reliable. In many tests, especially the longer term ones, we need to do water level corrections. So what do we get from the monitoring during the test? Are water levels if we are measuring them manually, or pressures if we are using these pressure sensors, the data loggers, which of course we can convert to water levels later on. The typical correction that we do is correcting for variations in atmospheric pressure. So we'll have, for instance, a bottle pressure transducer, which will measure this variation, and we use that to correct the readings we get from the other data loggers. But depending on the duration of the test, we may also need to correct it for rain, although we should always avoid to run tests when it's raining, especially heavily. And of course, in coastal zones, we'll have to account for the tides when we are doing these corrections. So talking of pumping test interpretation, what we get then from our pumping tests are what we call data curves or drawdown curves from the observation wells. And the analysis of a pumping test involves the assessment of these curves, which measure drawdown against time using type curves. And the type curves, then they will represent the theoretical drawdown that would be observed based on a set of assumptions used for any analytical solution. And what we do, we plot these both curves in log-log charts, and then we do an overlap and try to get the best fit possible. Well, each method will have a type curve, which are these analytical solutions. And the main system, which is the basis for all the other systems, in fact, is the Theis Solution, which was the first one developed for confined aquifers, looking at drawdown in transient conditions. Then we have a number of other solutions which are essentially derived from the original Theis tool. So for leaky aquifers, we have the Hydrostratigraphic solution. For unconfined aquifers, we may use Neumann, or we may use Theis with Jacob correction. And some methods have also been developed for double porosity or fractured aquifers, as well as multiple aquifer systems assessed during a pumping test. So talking a little bit about confined aquifers, this first solution, the drawdown analysis in the transient regime in a confined aquifer, then was carried out by this author, Theis, in 1935. And as any of these methods, they will all have a set of assumptions that allow us to take these ideal conditions into consideration. So in this case, we have a confined aquifer, extent of the aquifer infinite. Aquifer is homogeneous, isotropic, which we know for a fact hardly ever happens. Piezometric surface is horizontal pretest conditions, and so on. So there is a number of assumptions. And for confined aquifers, we also have these additional solutions, the Cooper-Jacob methods, which relates to situations, specific situations where we have longer times, for instance, looking at specific points during the test. And of course, we always assess, in fact, the results from recovery tests, which will be once we switch off the pump after the pumping period. So for the Theis method analysis, we'll need drawdown, date and time in each observation wells. As I mentioned before, we will need to know the distance between the pumping well, the observation wells, and the pumping rate, which in this case would be constant. We'll see that AquiferTest, the software AquiferTest, actually allows us currently to interpret tests even when we don't manage to get a constant pumping rate, and we'll look at that in a minute. And as mentioned previously, we'll get then for this aquifer the parameters of transmissivity and storativity, or specific storage, multiplied by the aquifer thickness. And these are key parameters when we are assessing any aquifer system, especially when we start looking into numerical models. So these are the sort of basic parameters that we need to know for a given aquifer or aquitard. So the Theis method analysis are based on two equations, essentially. One, which relates a drawdown to pumping rate and transmissivity based on something we call the well function, which is this WU. So in this equation, we have S as the drawdown, and once we solve this equation, we will get our results for transmissivity. So the well function is given by this integral here. Lucky for us, the solution for this integral has already been calculated, and it's standard values, and we have a table containing these values. So it's just a read from what you get in your chart when you overlay your type curve and your field curve. And then the second equation, this is where we are going to calculate our storage, again, based on these tabulated values of U versus W of U, which again is the well function. So the well function then is given by this sort of longish mathematical solution here. But like I said, like for us, it's all being tabulated, and these are standard values. And this is actually what AquiferTest uses to get the results we need from the interpretation. So when we say type curve for a given solution, then we are talking about plot of well function versus 1 over U. And then we can plot that on a log-log paper and get to what we need, which is this type curve, in this case for confined aquifers. So these are the two equations now simplified that we need to solve. So again, we'll get transmissivity from the relation between pumping rate, drawdown, and multiplied by the well function. And once we have that, we use the well function to get a value of U, which we then use to calculate the aquifer storage. In this graphic method, and this is the way we would do it if we were doing it by hand, we will have the chart for the type curve, and then we'll have our data curve or field curve. And essentially, we want to find or to look for the best match between our data curve, i.e. the data we get in the field, with the type curve. And this is more or less what it looks like when we do that exercise by hand, try to get this best fit. Basically, then we have two plots, one of the type curve, one of the data curve, both in log scale. The type curve will give us a relation between the values WU and 1 over U, and the data curve will give us the relation between drawdown over time. And when we overlap these two, then we end up actually two values or two parameters in the Y axis and two values or two parameters in the X axis. By laying the data curve over the type curve, which obviously it's a graphical overlay method, we'll select an arbitrary match point which relates all these four parameters. Normally we get our match point in a way that we have round values for the well function and for U, just to make our calculations simpler. So, and this is how we get, as a matter of fact, this is how we get our values to solve those equations from these match points. We know the pumping rate, we get the well function from this match point, and we know the drawdown, so we can calculate the transmissivity here on this first equation at the top. Once we know the transmissivity, then we can get our values of 1 over U, we can get the time, the distance between the wells, and then we can calculate our storage. As I said, then these are the two main parameters we get from interpreting in an aquifer test or a pumping test. So just an example here, for instance, a confined sand and gravel aquifer, 7 meters thick. Again, looking at homogeneous isotropic properties, we have a confining aquitard above, 18 meters of clay. Below, we have a confining unit. That means, let's say, a perfectly confined aquifer. Then we have a pumping well, which is fully penetrating. That means the screen interval intercepts the entire aquifer. And the piezometer then is 30 meters away, and we have a constant discharge rate of 788 cubic meters a day for 14 hours. So this is the data that was recorded during the test. So we have drawdown over time, and here we have already calculated this relation between time and distance square from the testing results. And using then the time and the drawdown readings, and we have the aquifer parameters, thickness, the distance between wells, the pumping rate, we use those values combined with the well function to calculate, to obtain our results. So first of all, again, if we are doing this by hand, we would plot our data curve in a log-log type graph, draw down over time. We would have a graph set for us with the well function and the type curve in this case for the Theis method. And here then we will do the overlay of the two graphs and get our match points. And then from our match points, we get the values of drawdown and WU for that match point. And in the x-axis, we get the values for 1 over U and time. So again, when we do this by hand, it's easier if we select a match point, which falls into where the well function is 1 and where this value of 1 over U is 10. It just simplifies the calculation. Then we substitute these values on the Theis equations using also the values from the test, specifically initially the pumping rate. And then here we'll calculate our transmissivity. Once we get our transmissivity, then we'll calculate our storage. So analytically, it's relatively simple to do, but it's important to understand this theory, especially when we are, trying to do this match of curves automatically. So again, in this example, if we get the values from our match point, we get the value of drawdown for the value here of 1 over U, and in the other chart, time over the distance between the wells squared, the value of the well function and 1 over U. So 1 and 10. From the pumping test, we know that we have a pumping rate of 78 cubic meters a day, and this will result then in a transmissivity value in this example of 240 square meters a day, and a storage value of 2.2 10 to the minus 4, which is pretty consistent with a confined aquifer. What I would like to cover now briefly will be the technique for interpreting pumping tests in fractured aquifer, specifically talking about this method Warren root, which is specified as double porosity in AquiferTest. So in terms of fractured aquifers, groundwater flow in a fractured aquifer can be very complex. So conventional pumping test solution methods that require porous flow conditions would be in principle not applicable. So one approach, and this is the approach that Warren Root take, is to model the aquifer as a series of porous low permeability matrix blocks separated by hydraulically connected fractures of high permeability. So if there is flow from the blocks to the fractures, then the fractured rock mass is assumed to consist of two interacting and overlapping continuous media, which would be formed by the low permeability primary porosity blocks and the high permeability secondary porosity fractures. The flow equation in the matrix, which is this equation that is shown down here, Q alpha, it assumes that the flow between the matrix and the fractures is proportional to the conductivity of the matrix and the differencing head between the two media. Alpha is a parameter that depends on the geometry of the matrix blocks and is related to this capital A parameter, which would be the matrix block surface, and V, which would be the matrix block volume, and L, which would be a characteristic length of the block. As we'll see, these are adjustment parameters. We don't, well, in AquiferTest, we don't have to necessarily specify these three parameters for the matrix block. So what we see here on the right, we have a drawdown curve in fractured aquifers, which will follow essentially three stages. The early stage, which is at the beginning of the pumping test, when the water is pumped from storage in the fracture system, and the matrix blocks at this stage, they don't affect the flow at all. So in the second stage, which would be the intermediary stage, then the flow to the well is somewhat increased by water released from the matrix blocks, while the drawdown in the matrix is relatively small compared to the drawdown in the fractures. So this would be this intermediary phase. And then at the late stage, you reach an equilibrium between flow from the matrix and the fractures to the well, and essentially the aquifer starts to behave as a single porosity aquifer and essentially follows the Theis curve. And this is the Theis curve, the type curve indicated here. And then and this is in the red dots, we see the curve from this pumping test and the observation well, and we see how it deviates from the Theis curve. So as I mentioned earlier, all these interpretation methods, they are based on those two initial equations from Theis. Now, continuing on this interpretation, we have two geometrical parameters, which are adimensional, which are lambda and sigma, and they characterize the flow from the matrix to the fractures. So for a given sigma value, varying the lambda, will change the time when the flattened part of the curve, which is this intermediate stage, when it starts. So the higher the lambda value, the longer the flattened section of the curve, and the longer it will take for the drawdown curve to overlap again with the Theis curve. In this equation, RD would be a dimensionless distance given by the ratio between R, which is the distance between the pumping well and the observation well, and RW, which is the radius of the well screen. And all these equations are basically on the premise that the matrix has distinct properties as expected of conductivity and storativity from the fractures. And then lambda and sigma essentially combine the two media by comparing storage between the two media, as well as the hydraulic conductivity. And in AquiferTest, and we'll see that in a moment in an example that we're going to show, different from the, let's say, standard porous aquifers, we will have ways to adjust not only transmissivity and storativity, but also we can adjust the values for sigma and lambda, and by that manner find the best fit between the field curve and the type curve. So let's have a look at our AquiferTest example. Okay, so this is the initial screen in AquiferTest, in the latest version. And it essentially follows a sequence of logical steps. And what we do is essentially following these menus from pumping test, going all the way to the right, where we finish up with the reports from our test. And it also has these sort of main menus up here, which are related to opening projects, creating new files, saving, etc. So at this first step, the pumping test tab, we will insert the project information. In this case, we are just calling fractured aquifer. We will insert the data from the pumping test. So just name, let's say, pumping test 1 and who performed the test and the date. And in this example, we'll assume a thickness of 100 meters for this fractured aquifer, which essentially corresponds to the length of the rock mass that is intercepted by the observation well. Up here, we define our units. So the dimensions will be in meters, time in seconds, and we'll work with the discharge in cubic meters an hour. And down here, we can enter the information from our wells, both from the pumping well and the observation well. We insert here the coordinates, and by inserting the coordinates, the software can tell or can calculate the distance between the two wells. And we have a series of properties that we enter here. Screen radius, for instance, casing radius, borehole radius. Because we are analyzing two wells which have been drilled as open holes in the rock, we'll just consider the screen length and the distance from the top of the aquifer to the bottom of the screen. On the second tab, we'll insert a constant discharge rate of 9 cubic meters an hour. In this case, a constant rate pumping test. And then we'll move to the next step where we'll insert our water levels. And you can do this by, for instance, importing from an Excel file that you have generated for this purpose. And when you do that, you'll see something like this, which actually shows the drawdown part of the test, and here we see the recovery. And we'll also insert here the static water level. When we move to the analysis, then what we'll do here essentially is select the method that we want to use, in this case, double porosity. And here in analysis parameters is where we can come then and adjust, the values, increase or decrease depending on what we want. Trying to find the best match. Another way, which is much simpler, is just to come here and select this fit, and it will just automatically search for the best fit between your field data and the type curve, in this case for the double porosity method. And once we do that, in this case we are looking at the results for observation well 1. Then we'll get here on the right the transmissivity values, storativity, and also the sigma and lambda parameters. Another feature that is it's useful in the software is this diagnostic graph, where it calculates for you the derivative of the drawdown curve. And then based on the format or the shape of this curve, you can actually compare it with some reference curves, which are given here on the right. And we can actually see in this example that this sort of behavior of the derivative, coming down and then back up. This is precisely what we see here for unconfined or double porosity aquifers. So it's just another manner for you to tell or confirm the type of aquifer that you're working with. So this very quickly is how you would do the interpretation of the results in AquiferTest. Following from the analysis, we can come to site plan, and here we can select the data that we want to use to create this drawdown curve. So in our case, we are calculating the results or calculating the drawdown based on the results at observation well 1 for a time duration of 10,000 seconds. And when we do that, we can actually see the drawdown curves based on the parameters that were calculated for observation well 1. And this is also a way by which you can use to, for instance, calculate the expected drawdown in a certain area of your certain sector of your study area. So you could, for instance, simulate like a virtual well, let's say somewhere here, and then you would have the drawdown estimated for any area here that you select. You can have the estimated drawdown in these sectors. Finally, we have the reporting tool, which is very helpful because it just reads from the information that you have entered before and the analysis. In this case, we're showing the analysis for the test. And then you can see all the information from the test itself. You can insert the logo from your company. And down here, you're going to get the results for the aquifer. And here we get both for the observation well and for the pumping well. We get transmissivity, hydraulic conductivity, storage coefficient, and the two geometric parameters. Remembering that because we inserted at the beginning that the aquifer thickness was 100 meters, then the hydraulic conductivity will be just the transmissivity divided by that. So it's, in this example, it's 2 orders of magnitude lower in absolute terms. Okay, so concluding this example, I would just like to show you another brief example, but now looking at an application where just the analytical solutions were not enough to solve a specific problem that we had. Okay, so to finalize this analytical solution part and interpretation, I'd just like to talk briefly about the limitations of these solutions. The main limitation really is that they are sort of, they follow sort of idealized assumptions. So, you know, assumptions that are common to most of these solutions are that the aquifer is horizontal and homogeneous, isotropic, infinite, constant thickness. Horizontal flow, you know, pumping wells are considered to be fully penetrating the aquifer. They do not take recharge into account and also have limited boundary conditions, situations that it can consider adequately. And as we know in practice, what we find is, or we most commonly find are, for instance, pumping wells that intercept multiple aquifers. Sometimes wells where the screen is intercepting just one aquifer, but then you have the sandpack in the annular space all the way up the well profile, and that connects you know, different aquifers. Confining layers which are not continuous laterally, and also irregular boundary conditions such as meandering rivers, or in a mining context, for instance, an open pit near the area of the test. So how do we deal then with these situations where we have this sort of, not necessarily less than idealized conditions, because that's the standard, but sort of more complex situations. So I'm going to show an example from southern Brazil, a study that we did a couple of years ago. And this took place in the northeast of the city of Florianopolis. You can see the geography down here, but Florianopolis is a city that is, well, a great part of it is in an island. In this study, we were assessing the productive or production capacity of an aquifer here in this sector where I'm putting the mouse on, the Ingleses aquifer. So what happens here is public water supply is based on abstraction wells, and in this public water supply usually meets the requirements of a population of about 40,000 people. But then during high season in the summer, this can increase up to 100,000, 120,000 people, 3 times. And then the objective of these assessments, as I mentioned, was to assess the potential for groundwater production from this aquifer, Ingleses aquifer, avoiding overexploitation and salinization of the aquifer by pumping saline water into the continent or into the aquifer. This is a north-south cross-section showing the local hydrostratigraphic conditions. Basically, we have a number of sandy aquifers, and these are separated vertically by these ectards, or low permeability layers. And then we have abstraction wells and piezometers spread around this region. So the comparison with the analytical methods, even though there are methods to interpret pumping tests with observation wells in different layers, such as a method called Hamler and Maas, they do not allow for pumping tests which abstract water from more than one aquifer. So this is an example of a sort of more complex situation where you would be limited, you know, by using the analytical solutions. So what we did in this case, we did start with the analytical solutions, but then we moved to something a little bit more sophisticated, with a representation of this aquifer in a 3D MODFLOW model. So following this is just a cross section in the west-east direction. Again, we see the aquifer layers, and here we see one of these aquithards that does not extend infinitely, but rather creates a sort of semi-confined condition here in this area. So in this example, what we did, we created a sort of simple visual MODFLOW model using a domain of 4 by 4 kilometers. And this was just to ensure that the drawdown from the pumping well would not reach the model limit. And then in this case, the numerical grid was refined down to, half by half meter cells here around the pumping well, where the pumping test was actually conducted. Here's that same sort of section that we saw in the hydrostratigraphical profiles. So that would be our conceptual model. This would be our numerical model. And here we have then again the various aquifer levels separated by aquithards. In this case, what we did was essentially use the numerical model to come up with aquifer parameters, for those for these 3 aquifers mainly, the 3 top units. That would represent the drawdown curves that were observed during the test that was done in the field. And we did this by using a inverse modeling technique and based on PEST. So in this case, we do the drawdown that had been generated in each aquifer from piezometers that were installed separately in each layer. And therefore, we could use the observed drawdown in the field to sort of back calculate the aquifer parameters that would result in the best match between simulated drawdowns and observed drawdowns, i.e. inverse modeling. And again, PEST is sort of the most broadly known algorithm and most used for inverse modeling. And it's a standard program or tool that comes with, that there is in Visual MODFLOW and FreeFlow, for instance. So in this inverse modeling approach, essentially, we try to get the best fit possible between the drawdown curves by adjusting the input parameters. So, that's sort of the cycle that we follow here, trying to get this best fit. So the calibration process using PEST, what PEST will do, it will try to minimize the error. That means the deviation between, for instance, the observed head in the field to the calculated head in the model. So it will follow a combination of, for instance, 2 parameters here, which could be the K values for 2 different units. And we'll look then for the minimum value of this objective function, which is sort of the error function. And what we see here are sort of isolines, on this field of possible combinations of one parameter and the other parameter. We can see that there are isolines of similar errors. And as you improve your calibration, your objective function sort of moves into this area here where we get this minimum error. And then once PEST reaches this minimum error condition, then it will conclude the simulation. So by doing this, we got this situation where we have the here on the right side, we have the drawdown that was measured in these 3 different aquifers, and the fit that we got between the field curves and the curves, the drawdown curves that were calculated by PEST. And this is what it looks like in profile. And here we can also see that you know, the size of the model domain was adequate, because we see that the drawdown, you know, for this condition did not reach the limits of the model. And by doing this, we were actually able to come up with values for both, for the three top units here, Aquifer 1, 2, and 3. And again, this is one example of a situation that you would not be able to get, let's say, to the best parameters by just using a sort of analytical 2D solution. And I'll take any questions now that you may have.